title of our research is Image-to-Image Diffusion for Underwater Image Enhancement. So for the big picture, our research heavily involves and implements the concept of domain transfer. So now imagine you are a UAV or an underwater unmanned vehicle that wants to track the number and species of fish you see on a live camera feed. You may consider using big computer vision techniques such as ResNets, faster RCNN, segmentation, or NERFs. However, these techniques work well with the above water domain, but are not so good on the underwater domain due to issues such as distortion and light attenuation. For example, you can look at these images we have here. We got both images from an underwater domain and an above water domain. The orange circles represent areas where computer vision models for the underwater domain may have trouble doing downstream applications on or truly analyzing. However, those same areas in the above water domain are far easier and able to do downstream applications on. So to solve this issue, we are doing domain transfer. Domain transfer refers to the challenge of adapting models to work effectively in diverse or challenging domains. Specifically, this concept involves problems where images are in a domain that is not the usual domain that image-based or computer vision models tend to work on. So for our research, it specifically involves producing better results by doing the domain transfer of underwater images to above water images. Throughout this presentation, we have some examples of what other groups have done to do domain transfer of underwater to above water and the challenges they faced, along with our own implementation and specific setup to do this.
Underwater study can apply to the ocean resource exploration, marine ecology research, naval military application, and biological monitoring. However, because of the light attenuation, turbidity, poor illumination, and color diminishing, it is hard to collect a clear image from the underwater. So to get the clear image, like in the middle, we are going to use the image-to-image diffusion model to convert underwater image to above ground images.
So we mentioned the image-to-image diffusion model, but what is it? A diffusion model has two processes. The forward diffusion process iteratively adds noise to a given image until it's completely noised. And then the reverse diffusion process trains a UNet to iteratively remove all the noise, and thus after enough steps, produces the target image. A UNet is a series of convolutional layers that are connected in a way where the image is sized down and then sized back up in a hyperparabola-like shape. Respective layers on opposite sides are connected together, which are what the gray arrows show on the diagram on the right. The uses for diffusion models can be in image generation, in painting, and text-to-image generation. To build off of diffusion, you can add a condition to the input of the denoiser. The condition can be text, image, semantic map representations, what have you. Multiple conditions can be inputted together for more information for the model to use. On the top right, we have an example of this where we have an original image of a face and then a text condition of red lipstick or beard. What's outputted is the original image with the respective change. So stable diffusion is a conditional diffusion model that we use within our research. Here in this demo, you can see you input a prompt, in this case, the statue of David riding a horse, and then that visual representation of that prompt is then outputted.
Yeah, so an example of one kind of image-to-image transformation would be instruct pix-to-pix, which is a method for editing images using human instructions. In other words, an input image is conditioned on a certain text prompt provided by the user. So this is a little slightly different than just stable diffusion because this method uses both a large pre-trained language model, GPT-3, and a text-to-image model, stable diffusion, to create these images. So here's an example of an online instruct pix-to-pix model. So what the user can do is input an image, as you can see on the left, statue of David, and then you can provide an instruction, for example, convert it to black and white, and then based on that condition, a new image is created.
CLIP, or Contextualized Language Image Pre-training, is a model developed by OpenAI which has learned an association between images and text. CLIP can understand images and their corresponding descriptions in a shared latent space. When feeding an image into CLIP, it outputs an embedding which contains all the important features of the image. This embedding can be easily read by computers, which makes it more suitable for downstream tasks. Specifically for our model, we condition on CLIP to make sure that the final image resembles the original. So CLIP guides our model towards the final image. Now, some previous approaches when trying to solve this domain transfer problem have used GANs, which is also known as generative adversarial networks. Other models are based on physics principles, so they basically try to calculate how exactly is light distorted through an underwater environment. Other models use 3D underwater modeling, where they try to model the entire underwater environment. And another model, which is an image-to-image diffusion model, which is most closely related to our model, features a dual UNet structure with a distribution transformation network. Now, the problems with these existing underwater computer vision models is that many of them lack generalizability or adaptability. Specifically, some physics-based models lack adaptability and are less effective when encountering errors other than light distortion or attenuation. Another issue is overfitting. GANs are most likely to be prone to overfitting because they don't have a general understanding of the above water and underwater images. Another common issue is that they can lead to the formation of artifacts during the denoising process.
All right, so to go over the goals of our model, we aim to reduce dependence on the structure of the image, and we do this by using a pre-trained stable diffusion model. And we also aim to create more accurate output images, and we do this by incorporating CLIP embeddings in our loss function. And so ultimately, our goal is to help advance the field of underwater computer vision and to provide insights into conducting more effective domain transfer. So as a brief overview of our solution, we use a pre-trained stable diffusion model to reduce dependence on the structure of the image and to put more focus on the structure of the scene. And also because a pre-trained model already has a general understanding of above water imagery. And so our model takes in the underwater image and a noisy version of the corresponding above water image as its input, and it's conditioned on the underwater image and the CLIP embedding of that underwater image. And our loss function involves evaluations through mean squared error and the cosine similarity of CLIP embeddings. So for our proposed diffusion pipeline, we first perform forward diffusion on an above ground image, and this is done by adding Gaussian noise in a step-by-step process. And then we perform reverse diffusion with our model, where we denoise that image while conditioning on the underwater image and its CLIP embedding.
So to go over our methods, our method will involve using a denoising diffusion probabilistic model, which will be used to conduct domain transfer and convert the underwater images to above water images. Specifically, we involve pre-trained stable diffusion, which has already been trained on primarily above water images. As part of our diffusion process, we will condition the noised input with our initial underwater image and the corresponding CLIP embedding of that underwater image.
So we use 3 different data sets to collect our data: UIEB, and then EUVP, and then U45. As you can see in the pictures on the side, these data set makes reference photo more clearly.
Yeah, so elaborating more on what Marcus and Neil alluded to, reverse diffusion or denoising is mainly what we train our model to do. We use a conditional UNet with pre-trained weights from Stable Diffusion version 1-4 to perform this denoising process. Stable Diffusion itself is already trained on line 5B, which is a dataset with over 5 billion images, most of them being above ground images. In order to actually train a model, we input our noisy above water image, represented as x of t+1, and concatenate that with our initial underwater image, y naught, and condition this on the CLIP embedding of the underwater image. So all fed into our UNet to form one step of backwards diffusion. So as for a loss function, we mainly do two things. Our mean squared error term ensures that our model's output A aligns with the target output B. As you see on the right, we define A such that P theta is our unit backwards diffuser and tau naught is that underwater clip embedding. We define B such that Q is our forwards diffuser. And so in other words, we try to compare our model's X of T to the target X of T. However, mean squared error itself is not enough to suffice. We further define four cosine similarity or clip loss terms that help mitigate applied noise and ensures a relationship between the above water and underwater images or domain. Cosine similarity terms are all negative so that we can maximize that similarity between image embeddings, and they're all tuned on their respective hyperparameters using grid search.
To evaluate the accuracy of our model, we use four main metrics: PSNR, SSIM, UCIQE, and UIQM. PSNR and SSIM are standard ways of evaluating how high quality or how high fidelity an image is. However, UCIQE and UIQM are specific to the underwater computer vision field. They are used to quantify the artifacts created from light in an underwater image, including color cast, blur, contrast, and etc., based on the human perception of image degradation. However, these metrics are based on subjective perception and may not be accurate in actually determining how much distortion there is within an underwater image. We use it as a way to compare our model to other underwater enhancement models.
So unfortunately, due to computational constraints, our model is still training at this moment. On the right here, we have some baseline images created using Hugging Face's Instruct Pixabay pipeline. And as you can see, they're not that great. We expect our final model to produce much higher quality and higher fidelity results than shown on the right. We further plan to run ablation tests to make sure the effectiveness of our clip embedding loss function.
So in conclusion, some of our takeaways are that we believe that clip vector loss function allows for the preservation of target characteristics and that our method is applicable to a variety of image-to-image transfer tasks. For the future, we want to improve applicability to real-time enhancement by reducing computational cost. Additionally, we want to fine-tune our model to distinguish between noise and image details and reduce the dependency on the quality of target images. We'd like to thank Blast AI for being a very important part of our research and providing the many resources and knowledge that is necessary for us to conduct this. And here we have our references. Thank you so much for listening to our presentation.